We are ready to restart. Do you hear me? Thank you. The next topic is about interworking IPv6 and IPv4. We have seen a mechanism last week that uses application layer gateways, HTTP tunnels and the like, web proxies. But there are also solutions that are at lower layers. Recall that we can analyze a solution and a problem as interworking when we really want an IPv6 host to talk to an IPv4 host, which in principle is difficult because the packets are incompatible. But we also have other problems, and this is what is solved partly with the application layer gateways that we've discussed last week. Today we will talk about one solution for this that uses mechanisms that are also used for like-to-like access. Like-to-like access, as we've discussed, is how can we use the IPv4 internet to interconnect IPv6 islands or vice versa. One very frequent solution that we use, in fact, in this course, but we could not have you benefit from it because we did not use the lab called Internet Engineering Workshop much this year. EPFL does not provide an IPv6 service over Wi-Fi, as you know. So we are exactly in this situation where we have an IPv4 service provider. That's the network of EPFL, for example, here. And we would like to run IPv6. For example, we have a lab, the Internet Engineering Workshop, INF 019, that has an IPv6 infrastructure here. How can we get access to the IPv6 internet? Well, one solution is to use tunnels. We could put IPv6 packets and IPv4 packets. For this, we simply need a friendly ISP, Internet Service Provider, that agrees to serve our tunnels here. There are some, for example, Hurricane Electric is one of them. So you can go to the website of Hurricane Electric and you say, I want a tunnel, and Hurricane Electric will give you a tunnel that then you need to configure. This is what we did in the Internet Engineering Workshop. We configured the router of this room with the IPv6 address given by Hurricane Electric and the configuration information that is explained here. When the V6 ISP gives us IPv6 service, of course, they need to give us an IPv6 prefix. In this small example, I assume it is this prefix here that they give to us. In addition, they must also tell us what are the IPv4 addresses of one or several tunnel server that we can use as endpoint of our tunnel. So this is our own address, and the provider must give us this address here. In addition, typically, they give also IPv6 address to the two ends of the tunnel, and then we can connect our IPv6 router to the IPv6 router of the V6 ISP by encapsulating the IPv6 packets into IPv4 packets that will have source IP address, this one, and destination address, this one here. So this is typically done without any form of other intermediate layers. So here it's strictly IPv6 and IPv4. In particular, the tunnel is not encrypted, which is fair enough because anyhow, the packets you send, if you want to encrypt them, it's your responsibility to encrypt them, but you can do that at a higher layer. So to the rest of the world, to Lisa, for example, Homer here, that is using such a tunnel, appears as a customer of Hurricane Electric because the packets will be put on the V6 internet from this point here. An interesting part of this is we receive a tunnel with an entire prefix. If we have a prefix /64, we can organize our subnet prefixes in this place here to have many, many subnets, which is what we do in the Internet Engineering Workshop. So here, the prefix length can be configured to be not 64, but a larger value, for example, 80, in which case we can have many, many IPv6 subnets here. So we're in business, we belong to the IPv6 internet here. So check your understanding. Lisa now sends a packet to Homer. We do a Wireshark at point 1. What do we see in the packet? What's your guess? I close the poll in a few seconds. The majority says D, which is correct. So at this point here, what we see is an IPv6 packet. So there is no IPv4 destination address of any kind. So it's an IPv6 packet, a pure IPv6 packet here. And the destination address is the final address, hopefully, because otherwise we would not have a true participation in the IPv6 internet. So the IPv6 destination address would be this one. So the correct answer is D. Of course, we could have A acting as a NAT, in which case we would have the answer C, but that's not in the spirit of IPv6, because we receive from Hurricane Electric an entire prefix, not just one IPv6 address. So if you receive a prefix, the idea is that we can use it without NATs, which will make things simpler, because as we know, NATs require care and don't always work in, or don't work in 100% of the cases. Side effect of this, if we assume that all links in this scenario have an MTU of 1500 bytes, what is the value of the path MTU between Lisa and Homer? So Lisa and Homer both run IPv6, but what is the size of the IPv6 packets that they can generate? I close the poll in a few seconds. I close the poll now. And the majority says C, but that's probably not correct. It's hard to know the exact answer because it depends on the size of the header, and the header can have options. But if we assume there is no option here we have an IPv6 packet. This IPv6 packet can be up to 1500 bytes in this part and in this part as well. But here it is put inside an IPv4 packet. So an IPv4 packet can be 1500 bytes, that's the assumption, MTU 1500 everywhere. But the payload of the IPv4 packet can be only 1500 minus the IPv4 header, which gives us the answer B here. If we assume the IPv4 header has no option here, then it will be exactly this value, 1480 bytes. So that's one of the reasons for having a smaller end-to-end MTU. For Lisa and Homer, there is no symptom of this. We just see that if the packet is 1500 bytes, there will be a problem somewhere. It will be discarded because IPv6 routers would not accept it. But of course, we assume that they will do some form of end-to-end path MTU discovery. So that's one of the techniques that is used. Probably that's the one we use, for example, in a setting like EPFL, where EPFL does not want to give us IPv6 access in Internet Engineering Workshop. So we bypass this by going through a tunnel provider. And each of you can try this. You can get for free a tunnel from Hurricane Electric. And here you are, bingo, you're on the V6 Internet, even if your provider does not give you IPv6. If you use Internet access at home over ADSL modems in Switzerland, you probably have V6 Internet using 6RD. So 6RD is an interworking technology that is similar to 624. I will describe 624 because it's easier. It's only the addresses that change. 6RD and 624, it's exactly the same as tunnel brokers, but they want to make it fully automatic, plug and play. With the tunnel broker, if you do a tunnel broker at home, you will need to configure somewhere in your machine the endpoint of the tunnel. And this is exactly what we wanted to avoid here. And also the prefix that you obtain, you will need to manually read what prefix is given to you by Hurricane Electric. You will not obtain it from DHCP. Here, in contrast, the idea is to make everything automatic. So it is based on two things. In the case of 624, we use a block of IPv6 addresses, this prefix 2002, because it was invented in the year 2002. I say 2002, which is incorrect. It's not the number 2002. It is the number with X digits 2002. But everybody reads it at 2002, so I'll do the same here. So this block is reserved for 624 here. So it's a block that's reserved for all IPv6 addresses that are derived from 624. Then, if you have a provider that supports 624, which is the case of this one here, it should also respond to this address, 192.88.99.1, which is also a reserved address that is reserved for 624 here. It's an IPv4 address, and here's the remote end of all tunnels. All tunnels have the same final address. It is, of course, a unicast address, but it is used in what we call anycast. That means that this machine here, the 624 machine, the machine that does the interconnection between the V6 Internet and the V4, so the one that's provided by my V6 provider here, must inject into the IPv4 Internet this IP address, so a prefix of length 32. Of course, there will not be just one that does it. There will be many, many machines in the IPv4 Internet will inject the prefix. And by IPv4 routing, we will go to the closest of these ones here. Of course, this B has a standard IPv4 address, so it will have multiple addresses to the same interface, one of them being this one. Why does it help? Well, when I have to set up my tunnel here, I know my IPv4 address here. I know the end of the tunnel is exactly this one, so I don't need to configure anything specific here. So if I run 624 software in my machine, I don't need to configure any tunnel, in fact. That's the first thing. Second, the allocation of IPv6 block is also done automatically using this block here. Remember when we had a tunnel from Hurricane Electric, we need to go to the website of Hurricane Electric, ask for a tunnel, and then we get on this website the prefix that they give to us. So this is manually done, and we need to feed that into our DHCP and our numbering plan. Here it's done automatically by the rule that the prefix here, 2002, is a /48 prefix here, which means that we can add to the first 16 bytes 32 bits, the first 16 bits, we can add 32 bits, which are copied from the IPv4 address here. So for example, if we use 624, which we also did some years for the Internet Engineering Workshop, we automatically get the IPv6 prefix, which is 2002, followed by the 32 bits of our IPv4 address, which in this case will be 09080706. So we get both automatically. We get a block of IPv6, a block of /48 block of IPv6 valid addresses, and we know where to tunnel them. So when a packet goes from Homer to Lisa here, Homer will create a packet with destination address Lisa's IPv6 address. Now, by the internal routing in this local area domain, it will go to the default route that goes to the outside. It will go to router A. Now, A knows that it's a 64 router. It knows that this prefix is not a 624 prefix because the 2002 doesn't start with 2002. So I need to send it over a tunnel here. And I will send it over a tunnel with IP destination address, this one. I don't need to think twice, it's always the same. So it will end up into a 624 relay router, one of those routers that responds to this reserved IPv4 address. Now this 624 relay router will have a destination address, which is this one, and it will go over the internet, and a source address, which is here. In the reverse direction, when a packet comes from Lisa, we will analyze the destination address, which is 2002. Now 2002 is the well-known prefix, so all the relay router must inject into their v6 routing the 2002 prefix, very much like they must inject into the v4 routing this host route. They must also inject into the v6 internet the prefix 2002/16. Which means that by IPv6 routing, this packet will go to the nearest 624 relay router, which might not be the same as B. The nearest was here the nearest from the IPv4 viewpoint. Now it's the nearest from the v6 viewpoint. You will reach this router. Now this router receives it because it responds to 2002. It has injected 2002 into the internet routing. It receives it. Now it knows by analyzing the destination address, it's a 2002, oh, it's a 624, so I should send it over a tunnel. Which endpoint of the tunnel should I use? Well, that's a trick. I know from the IPv6 destination address, 9876. I know the tunnel is 9876, therefore it will reach Homer's router in the Internet Engineering Workshop without any configuration of B nor A. So this is the beauty of 624. And for many years, that was the preferred mechanism for provided IPv6 service over an IPv4 infrastructure. Now it's been replaced by a variant called 6RD, 6 for routing domain, I believe. It's similar, but the only thing that is changed that those two blocks, the 2002 block and this prefix here, which is in fact not, I said, it's not just one IP address, but several of them. They are, in 624, they are well known. They are the same for everyone here. Everyone has the same end of tunnel here, and everyone has the same 2002 here. Providers don't like this. Why? Well, because providers don't like to do the work for others. If a v6 provider is lazy, they might say, oh, I don't want to do 624 relay routers because all my customers, they will go to, via v6 internet, to someone else's IPv6 624 relay routers. So they serve as transit. Those who do the 624 relay router will serve as transit for those who don't do it here. Of course, you can play with with a BGP to avoid this, but it's safer if you don't do it at all. So what is done today is that we keep the same idea, but those blocks here are provider dependent. For example, Swisscom allocates a block, which is the block like 2002 for the 6RD block, and an IPv4 block also. And those are blocks inside the Swisscom set of addresses. So they will do this only inside Swisscom. If you're a Swisscom provider, Swisscom customer, you will receive IPv6 service over IPv4. And in fact, this is how Swisscom and Sunrise, as far as I know today, provide IPv6 service through some software in your modem that will do the 6RD thing. And then you have IPv6 at home, even though their backbone is still IPv4, which is, as far as I know, the case today. So this is the story of tunnels and how it works with provider tunnels here. In the lab, we've noticed that we've used Miredo. Miredo is, in some cases, if you're at home and you have no IPv6 access, then in the virtual machine, you can activate Teredo, and we configured it to activate it by default. It's called Miredo when it's in Linux, but the official name is Teredo. Teredo is a variant of all this that fixes the problem of NATs. In fact, in everything I said before, in particular for 624, I gave the example of the Internet Engineering Workshop, but you can do it also at home by running 624 in your PC. If you run 624 in your PC, you will automatically obtain an IPv6 address, which will be 2002 concatenated with your IPv4 address, and that will work, except you're probably sitting behind a NAT, and the IP address that you need is really the one of your NAT. You need the NAT to do this. Now, if you're not able to put 624 in your NAT, then you have a problem. This problem was fixed by having a variant that's Teredo. Now, we have NATs in NATs because in Teredo, we have even a virtual machine inside a physical machine behind a NAT. So that the 624 thing would be hard to make work, although it can make it work, but we need a lot of configuration. Instead, there's an alternative that was originally deployed and invented by Microsoft, in fact, and that works whenever there's a NAT. But as usual, when there is a NAT, we have problems with knowing the IP address and also perhaps trying to guess what exactly the NAT will do. So Teredo requires servers. It requires servers for your Teredo host to go to the server in order to discover what kind of IP address it can use. So this requires some infrastructure that originally was deployed by Microsoft. Now Microsoft changed their mind. They don't want to support Teredo anymore, so they don't support it anymore. Microsoft prefers to solve the problems of interworking with tunnels. We've seen web tunnels last week, so this is the preferred solution of Microsoft. They say if you don't have IPv6 access, well, you should configure a box somewhere to act as an application layer gateway and a web tunnel. That's the Microsoft solution. But some people thought Teredo is still an alternative if you don't want to use those tunnels. And there are people that provide Teredo servers here. Of course, the performance is not professional, so you don't expect to work Teredo for production environment. But if you want to test IPv6 access, like we did in the lab, in the virtual machine, this will work here. But other than that, it's conceptually similar to 624. Voilà, that's the tunnel story. And as I said, many accesses given by IP service providers today are really using 6RD, which is a variant of 624. But some providers provide more. They go beyond because they want to solve the problem truly of interworking. So a quite widespread solution is called 464XLAT. XLAT means translation. For some reason, X means trans. So that's a translation of 4 to 4/6. Here's the scenario. The scenario is you have IPv4 systems here, and you want to talk to an IPv4 remote customer here. So why would you like to do that? Well, perhaps because you don't have IPv6 access, but perhaps also because some services are available only over IPv4. So if you go, for example, to Google Scholar, strange enough, I mean, Google is one of the leaders in the IT world, is not able to provide their Google Scholar service over IPv6. So if you want really to access it, you need either an application layer gateway, a web tunnel that will go for you in IPv4, or you run IPv4 in your machine and you need to have an IPv4 access somewhere. Some applications like Skype are also very reluctant to deploy IPv4, so many implementations work in some Android phones, for example, work only over IPv4. So for such cases, there is the solution of translations, which does not use tunnels. It's very similar, but it doesn't use encapsulation. So here is the scenario. Again, I repeat the scenario. I have an IPv4 network on the left that is connected via, for example, my ADSM modem to only IPv6. So it's not the situation in Switzerland today, but it will be the situation in some years when the population of the world continues to grow and there's not enough IPv6 addresses. And you want to connect to the IPv4 internet. Of course, we could do a tunnel of IPv4 and IPv6, but since tunnels cost headers in headers, the idea here is to avoid the tunnels by translating the header. So those two boxes here, your ADSL modem that must be configured as a so-called CLAT, C stands for customer translation, will not do a tunnel, but will translate the IPv4 header in IPv6 header. In fact, this is very much what we do already today with a NAT. If you think about it, a NAT is translating your IPv4 header into another IPv4 header, which normally a router should never do. So that's the same idea here, except the translation will be 4 to 6. And here, the PLAT stands for the provider translator, will do the reverse translation here. The PLAT is also called a NAT64. For some reason, the CLAT, which is a NAT46, if you want, but is not called in this way. So how does it work? Of course, this is all supported by the provider. So the provider programs your ADSL modem to do this and will provide a number of things. First, it will reserve a block of IPv6 addresses to represent the IPv4 internet. It's a bit like we did before with 624. We saw that there was one IPv4 address or a block of IPv4 addresses that were used to reach the IPv4 internet. Here it's similar, but it's supposed to be a block that's large enough to represent all IPv4 addresses. 96 plus 32 gives 128. So you need to reserve a block of /96, and then you can map the entire IPv4 internet in this block. Now, because it's provider dependent, this block is given by every provider. Second, we need to give to every customer that is receiving this service here a block of IPv6 addresses here. So for example, now that block can be it can be with a very long prefix here. So for example, here I'm allocating to this guy this prefix. That's business as usual. I am an IPv6 provider, so I allocate an IPv6 prefix to this guy. Now this guy happens to run only IPv4, but other than that, it's no different. Third, we also need to allocate a block of IPv4 addresses to be used by the IPv4 internet to represent the IPv6 internet. So those blue addresses here are IPv4 addresses that I will use to represent guys like Homer here that are in fact not reachable over the IPv4 internet because they reach the internet only through me and I am only an IPv6 provider. Okay, so that's the starting point. Now, this box here will translate from IPv4 to IPv6. That's very easy. It's very easy because IPv6 is large here. So for example, when Homer sends a packet with this private address, for example, I'm showing 10, typically that would be more 92, but that's easier to do the translation with those 10 dot addresses. So Homer sends a packet. The box here, which is like a NAT, will replace the internal address, which in this case is the source address, 10.1.2, into an IPv6 address, which is belonging to this block here. So here it will be, so this block is typically larger than 96. The prefix is smaller, which means the block is larger, because there might still be IPv6 addresses here. But here we ignore that. So this green address is replaced here as a source destination address by this one here. It's a NAT job, but it's much easier job. It's completely static. I simply put in the lower bits of the IPv6 address exactly the IPv4 address here. Now the destination address, so Homer is sending a packet to Lisa, 9876, will be mapped now into this block here which is reserved by this provider to represent the IPv4 internet. Using the same mechanism, is blocked algorithmically. So the mapping here in both directions is very easy. When a packet comes back here, it will, if a packet comes to Homer, then this CLAT knows that this prefix is reserved from the IPv4 internet and will translate the IPv4 address and put an IPv4 packet on this network here. In passing, we see that we can reuse all kinds of IPv4 private addresses in this mechanism. There is no problem here, at least for the green addresses. So that's the customer-side translation, which is very simple. On the provider side, it's not as simple because now we're translating IPv6 addresses into IPv4, and the space of IPv4 is smaller here. So for example, when this box has a packet that comes from Homer, this is the source IP address it will see here. Now, it will need to map it into one of those blue addresses. Those blue addresses are the addresses that the provider uses to represent all its IPv6 customers to the IPv4 internet. Then it will, in order to do that, of course, the size here is larger than there. Therefore, we will need to use the trick used by NATs, which is to reuse multiple addresses. There are fewer blue addresses than combination of red and green addresses. Of course, there is not only Homer. The IPv6 provider may have millions of Homers here. So there will be many red different prefixes. So he will also, to save the number of addresses, the provider will also use the port number like a NAT does here. So this is called stateful address translation because we need to remember, like a NAT does, the allocation that we did, and we need also to modify the port numbers in case there would be a collision. In the other direction, the destination address here, there is no problem because this address here that contains the blue destination address could be algorithmically derived, so there is no problem of translating the IPv4 destination address and nothing to remember. It's completely stateless. So I said stateful because here the PLAT will need to remember in its table, for example, that this address here, the IPv6 address that combines the red IPv6 prefix and the green translated IPv4 address with a port number, has been translated to an IPv4 address, and the port number may need to be translated in order to save on the number of blue addresses here. So the PLAT is in fact a NAT. It's called a carrier grade NAT. That means a big NAT. We've seen an example of that already. For example, we saw that the EPFL internal network uses private addresses using the similar mechanism here. The address block 1.64/10 is in fact reserved for exactly this use here. We don't use 10.something addresses in order to make sure we never get collisions with the customer addresses. So this block is reserved for these translation here. And then it's private to this carrier. So Swisscom may reuse the same block as Sunrise because they will do this only inside their domain. Okay, let's test our understanding here. When Homer on the left sends a packet to Lisa here, and Lisa responds, and we do a Wireshark at the source at Lisa, what will we see? I close in a few seconds. And the majority says B, which is the correct answer. The correct answer is B. There is no IPv6 packet here. So we have only an IPv4 packet, and the destination address is one of those blocks that represents all customers here. We observe the packet at 5. What if we observe it at point 3? What will happen? I close in a few seconds. And there's a tie between B and E, and the correct answer is E, which means both B and C. So this packet here is an IPv6 packet. So its destination address must be exactly this one here. So, and this has been done by the NAT that has it in its table. And the source address now is very simple. The source address was 9876, but remember, the provider reserves a block for algorithmically mapping this IPv4 internet into IPv6, so it will do the same here. Now this is stateless. Obtaining this was stateful, but we will need to do both so that we truly have an IPv6 packet that can be used and correctly received by the intended destination. One last question on this topic. Again, the question of MTU. Assume all links are 1500 bytes everywhere. What is the path MTU for Lisa and Homer? I close in a few seconds. The majority says A, but this is incorrect. The correct answer is probably B. Why is that? Well, the IPv4 packets, they must have a maximum size, okay? But those packets will be translated into IPv6 packets in the intermediate points. During the translation, the header becomes larger. So if you had a packet of 1500 bytes already, then your IPv6 packet will become 150/20 bytes. So that will not work because we said the MTU is 120. So you need to anticipate this, and you need to make sure that your IPv4 packet is at most 140/80 bytes here, right? Which is the same value we had before with encapsulation, but it's in different setting. Before we had the same value for IPv6, right? An IPv6 MTU of 1480 bytes means that an IPv6 payload is 1440 bytes here. Whereas here it's an IPv4 MTU, which means that the payload is 1460 bytes here. So we still have gained a bit. If we had done encapsulations, of course, we would have lost more bytes here. But in all cases, we need to account for this. So you see, it's risky to always assume that an IPv4 packet can be the maximum size. Voila, we've seen the main parts of the interworking, but with a little add-on, we can use the same system, not just for providing 4-to-4/6, but truly for interworking. In fact, the two problems are closely related because probably the problem is when you want to go to a server like Google Scholar or the InfoScience of the University Agostinho Neto, that here works only on IPv4, like all InfoScience service of the world. For some reason, they use IPv4 addresses hard-coded into their authorization system here. But probably here, if you have IPv6 service, you probably have IPv6 everywhere. Also, you might have IPv4, but you also have probably IPv6. So, but the problem is I want to go to this server. The server is only IPv4. One way I could do it is, of course, to run IPv4 software in my machine and use the previous solution. But another way here is to reuse exactly the half that we had here, the PLAT, which is a NAT that translates IPv6 to IPv4 header here. So with the same solution as before, the same reservation of a block, we can work in the same way by saying, if I want to send a packet to this machine, then all I need to know is to create a packet with destination address, some destination address that is in this block, so mapped in this block here. So I will send to 2001 Baba B0 finished by 9876, and this will find its way to this PLAT, because of course the block here has been reserved by this provider, and the PLATs inject into the routing of the providers which prefixes they respond to. And then the PLAT can then translate the IPv6 source address here into an IPv4 address that is in this block here, reserved for representing the IPv6 customers here. So very much the same as before will work if we do it natively now over IPv6. Now we don't need the CLAT here, it's a bit simpler. We don't escape the complex carrier grade NAT here. And for this guy here, the server 4 will appear to be as an IPv6 address, which is this one here, which makes sense because IPv6 addresses are large enough to be able to embed IPv6 address. There's still one catch. How does client 6 know that it needs to go to this IPv4 embedded IPv6 address here? Well, as you can guess, well, the solution is to use the DNS. So the provider here that provides this service, so this service is given to you by the IPv6 provider, who gives to you only IPv6 service, so still wants to allow you to access the IPv4 old-style internet, will provide you the PLAT function, and will also manipulate the DNS by, whenever you do a search by going to the DNS server of your provider to this final destination that works only on IPv4, then this guy knows it works only on IPv4, and now the DNS will obtain the IPv4 address and is synchronized with the block that is given to this provider and will respond to you with an IPv6 address that embeds the IPv4 destination. So for this guy will not even know that the destination is IPv4 only. It will get an IPv6 address and everything will work perfectly. The price to pay is to have carrier grade NAT and DNS manipulations, but this is what is done by IPv6 providers who provide v6 only service. Voila. This is all we will see today on the transition and the tunnels and the deviation. So we've seen a number of mechanisms for transitions. All of them are deployed today, depending on the environment. The 4-to-4/6 slats, there are variants of that we didn't go through it, but you can go through them if you need them. NAT 6.4, DNS 6.4 are the crucial elements. The tunnel brokers and 6RD are the other elements that we obtain if the only problem is to get access to the v6 internet when we have only v4. Those other elements are the converse problem. If we have only v6 access and the rest of the world is not entirely v6, then we do this. This can be complemented with proxies, application layer gateways, that are either on the customer side or on the server side. This is typically done in enterprise networks. And some devices, for example, Android devices, typically provide the CLAT inside the device, so that if you have a mobile operator that provides IPv6 only service, then your Android device will be able to work and access IPv4 services, for example. iOS devices are a bit different. Apple assumes that everything should work with IPv6, so you will not be able to go to Google Scholar over IPv6, but the Apple way, you are not necessarily compatible with everything. Voila, that's the conclusion for today. That's the end. So take care, stay healthy. Get prepared for the exam by doing the mock exam, which again is not really a repetition of the exam, but only a repetition of the infrastructure you will need to have for the day of the exam. Thank you very much et bonne journée à tous.